quality. And when you guys look at like a filter, how it looks and have a kind of feeling. So we have different kind of filters. And basically the filter is what they are doing is separate valence. And we have two here, and we can see the different in colors. These two are at around 600. So yeah, this 5, 6, and this is around 600. And we have another one here and around umbrella here. So apparently they look different. So what we are seeing is the refraction from the bottle. So like this blue filter, the blue line will come through, and we have this like yellow come through. So basically that's the filter. And we also have a dichroic. This is a mirror. So this also separate by the valence. I don't know if I can find better way to do this, but let's try now. So let's take this on. Wait a minute. Yep. I can go right next, but let's see which way it goes up. Yep. So what's going to happen here is I have line of different valence coming hit this way and reflect up, and this is actually a combination of blue and green. So this is a dichroic mirror, which by the definition it will reflect the short valence and change with the longer valence. And I think I have a piece of paper here. Can someone turn off the light so we can see it a little bit? So you can see the blue is reflect in this direction, but we have some yellow coming up. So actually they are separated by the valence, and that's like a very basic idea of dichroic mirror and the filter. Okay, the lights back on, thank you. And I think we can start from the illumination here. The reason we need the filters is because for the fluorescent imaging, we use laser for the excitation, and then we have our probes, Sci3, Sci5, LX, whatever. It will emit photons in different valence, and then we have different valence we can separate with our filter sets. So the changing of the filter set is the most complicated part of the experiment. So you know your emission, your excitation, and then you can choose the right filters. So we start from the illumination here. So I made like a switch for all here. Everything is connected to this main power. Computer is not, computer have a separate power. So you don't need to turn the computer off every time. But these need to be on at the beginning. And we have this blue and the red and green laser. This is a switch for the blue, you turn on. But you need to make sure this key is turned to the standby mode here. And you need to wait for like 2 or 3 minutes until they stop blinking, and then you can turn it on. That's like kind of warming up for the blue laser. And this red and green, you can just turn it on. And now we wait for these to warm up, and then we can switch to on, and then we have our illumination. So once we have this ready, let's take this apart and then see what happens down here. So you can see we have 3 different lasers, red, green, and blue. It's still blinking, which means it's still warming up. And then we will see, so it's going in this chamber, and we have different entities, which is a neutral density filter. We have OD of 4 and OD of 8 for every channel. And when you put it up, is not in the pathway, which means the light will go through totally. Then you push in, we decrease the intensity and another decay. So because the laser here is already very weak, so in most of the time we want this neutral, this filter being pulled up. So now this is steady. We can turn it on and we will see blue light coming through. So red is a shutter here. So the shutter is to decide which laser want to pass through. You can pass through 1, 2, or all of them, and it's controlled by shutter control over there. I will show it later. And then if you go out in this fiber, so this is our illumination. All these 3 lasers will go out in this fiber, and then it connects to the TIRF module in the microscope, and will go into the microscope, and then it can reflect up. So, yep. And then if we look at the microscope here, we have 2 different turrets. One above here and one bottom. The bottom one is for the TIRF, which is connect to that fiber over there, and this top one is connect to this LED, which is for our ABI illumination. By ABI, ABI illumination it means light is going through our sample, and by TIRF it's going in an angle and then reflect, total internal reflection, and only a very limited amount of energy is going into that penetration depth, and that's where we excite our probe. That's why what we have very high contrast. But yeah, the difference is the abyss in the top and the TIRF on the bottom. And then we have power control for either of them. Here is the shutter for laser. We have blue, green, and red, and then you need to turn this power on before you want to operate it. And blue on. Let's see if the blue light is coming through. And then because the laser go through like different filters inside this torus, so sometimes you turn that on, no laser is coming out. That's okay, because you might have like different filter sets here. But a very direct way to see if the laser is work probably is inside this. So you can put like a piece of paper in, and then you turn it on, and then it's here. Maybe you can turn the blue off and then turn the green. You can see different. Yes, it's green, and then green off, and then we have red. And you can turn all of them on together. You can turn all of them, yeah. So which means that's a combination of purple, kind of. So yeah, that's the way we control the laser. And then this LED is using for IRM and go through this ABI fluorescence. And here is the power controller for that. We have, if you come over a little bit, we have on, so we can turn the main power on, and then you can select like 3 different channels individually. So unchecked, it's going to be like blank, and then this blank means, so right now nothing is going out of that LED, and you can select either of them. This means we have the yeah, it's green, so green is on, and maybe we can see some green light here right now. Yeah, actually you can see it inside this. Yeah, it's green, and then if we like have this one on, say blue, becomes blue, and yeah, we can have them like yeah, sure. Yeah, that's fine. So for now we have 3 different lasers and 3 different wavelengths from this LED. And we use different lasers to excite different dyes, and also we use this for IM. And generally speaking, the shorter wavelength for the IM is the better for contracts, because our IM, the signal is from the scattering of the particle. So the shorter the wavelength, the higher scattering. So we have more signal from shorter wavelength, which is our blue. Which means if we are imaging our microtubule, we should use blue. That's the better one. But if you are doing gold nanoparticle imaging, which is because gold resona absorption the green light, which means green light is better for gold particle checking. Gold particle kind of have rational absorption at around 530. So green light for gold particle. And if you want to check gold particle level motors working on microtubule, and then you can do eye there. So okay, so coming back to the illumination, for the laser control, there is like a safe protection thing for this microscope. If you see, there is a cable coming out of this controller, and actually it's connect the microscope to this. And if I turn this off, so now our laser is on. If I have blue, let's see. Yeah, right now you can see the blue laser is coming through here. But this is a switch for like if you want to see the sample through the eye or through the camera. So if you switch to this binocular, which means which means the light will come through this. And then it's dangerous because if you have like very high laser intensity, the laser will reflect to this, and it will damage your eye. In that case, this system will force the laser to turn off, which means if you switch this to bino, laser is going to be forced turn off, and you lost control. It's not this one to your control. So make sure you want to switch it back to the confocal, and then you can have red, green, and blue going out. And yeah, that's the tricks. So illumination, and then all the illumination need to be go in very fine adjustment, or reflect to a very precise precision to do its works. So if we start from the IM here, we have 2 adjustments. Like if you go this direction, and I will show it over here. We have 2 aperture here, something like this. We can change it like wider, smaller, and it's located here. So this one is for aperture average 2/3, and this is for a field diagram. So the difference is the field diagram, by definition, it will change the field of view. Made it smaller here, you will have a smaller field of view, and you can expand it. And this is aperture diagram. It's a little complicated to explain, but you can image that light coming in the objective, and then from angle. Then this aperture is going to change the angle, so you can form it like wider angle or smaller angle. And this will affect the ratio to noise for our IM. And I have already like make a label and say this aperture set to like 2/3, and if you see your signal is going via, check this one. So by 2.3 it means we have like this small grid So this is 2.3 is kind of arbitrary, but it's somewhere around here. So 2.3, I text it and it's like the best contract. And this is the field of view. Also just set it to 2 and it's there. So this is the 2 control. You mean interchange these two? No. I mean you can change this to this, but you need to like readjust it because the center of the aperture is not exactly the same. So yeah. And last but not least, we have this filter. Now we go back to the filter. We have 2 different filters by now because mostly we use blue for microtubule and green for our gold. And it goes into these 2 slots. If you have your if you use blue for the microtubule, just put blue in, and this is going to be a little bit out. Because if you have both coming in, which means this allow only green and this only allow blue, and you have nothing going out eventually. So that's the point. So the person is interchangeable, so you can put these 2 here or swap it. That's fine. So let's try.
The filters do what? They just dampen the signal?
Yeah, it dampens a little bit, but also it narrows. So this LED, it goes out like a spectrum of kind of broad in spectrum. When we say like green, the center should be in like 520 nanometer, but it can span out like 100 of nanometer. So we need to use this filter, we call it excitation filter, to narrow down that expansion. So the narrower the expansion, the better the signal to noise, because the expansion of the wavelength is going to mess up the signal to noise. And that's why it is here. And then we have our half an hour, sorry. And then filter sets. This top we always set to 1, and by 1 if I get it out here. So yeah, what's inside is something like this. When you rotate to 1, and this cube will set exactly like in this position. So like in this. So you can see this is a mirror, and nothing up, nothing is here, nothing bottom. So just a mirror. And this mirror reflects like 10% of reflection and then 90% of transmission. So when the say green light come in this way, it will get reflect to our sample, and then both the scattering and the reflection will coming back, and when it hits this mirror, 90% of the intensity will go through. So that's it. And because we use only this channel for IRM and we never change it, so let's put it back. And we have one. So let's try to put some microtubule. Maybe you can see it. And then this is really the very beginning of the very beginning of the movie. But the oil is kind of arbitrary. You can put 1, 2 jobs. Rule of thumb is to at least have a very thick layer between your sample and the objective. I normally do 2 jobs. Why not? And then when you put on your sample, you can do it like directly this way, but it's better to do it in this way, which means I'm going to put this, contact this holder, and then do it like from one direction. In this way, you can push whatever bubbles, so there's not going to form any bubble between the sample and your and the objective. because when there is a bubble, so if we ever have any bubble, it's going to push to the periphery. It's not a good demonstration, but yeah, if there's bubble, you will see very weird image forming on the sample, which means if you have like weird image, then just check bubble. So now let's turn on everything. Okay, I want to show how IRM works, so I need to turn on the camera. This camera, we have this USB connect to the computer. We have the power cable to there. So once the main power is on, there's another switch over here. Maybe you go out there and can feel it here. There is a button here. That's the switch. Push it, and that's what's going to happen. Dun, 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 it's connect to the computer. And you might need to wait for a while, like 30 seconds or something, to turn on the software. And there's two different software to operate the camera. There's a Shelly and Shelly, which is kind of more complicated control, but it also has some image processing. Maybe we need to do a separate tutorial on this. But the easier version is the micromanager. Just micromanager, and then there will be a configuration file called andor.cfg under this folder, and just load it. And I have already set like most of the parameter default, like EM switch on. So EM switch, this EM is electron what EM? Multiplied, right? So this is need to be on because we need to set the gain. This is like define how many electrons will we get once a photon hit our camera. So the higher the gains, the more photons we will have. But also higher gain means we also have higher noise. That's kind of you need to balance. And frame transfer is a cool technique, which means so we all know that we have like 37 delayed on the camera. That's the time it needs to transfer a frame from the camera to the computer. And there's a technique then we have like a operate in one frame, and then it switch all the charge to a second frame, and then this one will continue expose, and then it will read out, and then it's like a backup frame. So read out and exposure is going to take place together, and you don't feel the lag time. So frame transfer need to be on to for higher frame rate. And again, I always set 300. It's about consistencies, and also you don't want to set like higher 300 because higher gain means higher voltage inside the camera, and it might damage the camera also. And then this is like temperature set point minus 70, and exposure is kind of depends on your velocity of your motors and frame rates, and then.
So that already includes the lag time.
I never calibrate this, but the lag time, if you have this frame transfers on, it's going to be negligible. I think it's very fast. But I think I can do like a calibration to see is it real frame rate. But for now we just turn it on, and you just click, so close, start from beginning live, and you're going to preview the images. There is a button here, auto adjust the contrast, and also you can do this auto stress, and it's going to auto adapt to the contrast. So now do we have our let's do blue. Okay, we have our blue light coming out. And remember, we are using blue, so blue filter. Okay, it's already a blue filter. And then this is set to 1, which is right. However, we have this filters down here need to set to 5. So when we are doing IRM for microtubule, we set to 5, and in that cube it's empty, nothing is there. So, and now if we look at the movie here, find the surface, and that's a trick to find the surface. Very good one. I'm proud of it. So we have like 1.5x here, and also we have a 1x magnification. So this 1x and 1.5 is like an additional magnification added to this system. By 1 it's like a smaller, 1.5 bigger. So by 1 you can see here the field of view. It's our exposure. So we're gonna I just adjusting the focus, so we can focus on that. It's too much. Yeah. It was really hard to find a surface in this system, but right now it is better. So if you push the objective down from like to the floor and then start to go up, and then if you go to that screen, as you're going up, you will see a hexagon going to expand from the center, which means you are approaching the surface. And like right now, you can go to this fine adjustment. This is connect to a motor inside this camera, and it goes like microns. So if you're going up a little bit, and then we are on the surface. We are on the surface when you find the rays a very sharp edge on this. So whenever this is in focus, you are in focus. Regardless if like there's nothing in your sample, you still know there's my surface. And here is easy. This is going down and going up, so no big thing here. So once you find your surface here, then you don't want the back edge around, and you can switch back to 1.5, and I think we normally do 1.5x. And the difference between here is 1x, we have 87 nanometer per pixel, and 1.5 is 58. And yeah, then you want to adjust the illumination. Generally speaking, the higher the illumination, the higher signal noise you're gonna have before you saturate the camera. So I just increase it. Increase, and if it's not changed, next when we start to use this anti-filter. This going pull this out, and we have just one ND inside the path, and it's brighter. And if we go all out, and it's separate. So you need to like kind of balancing with these two NDs and this power adjustment, and then get like some certain mean intensity in the movie. So yeah, let's do this. Yeah, we have microtubule there. So playing with the anti-filter and this intensity control, the target is to I would normally target at a mean of like about 40,000 here, because it's a 60 pix, it's going to be 65535. That's the maximum. So and then you want to have like a very nice Gaussian here, which means our intensity is uniform in this frame. So we just went through the IM part, and then we want to go to the TIRF. So ideally, we want to remove this reflect mirror to make the most of the TIRF signal, because we have like 10% loss of intensity with this mirror. But I kind of insist to put it in the same place just to minimize some like drift or image overlap problem. So just keep this on 1, and then is the neighborhood set to 6, and we have our 2-light TIRF. So by definition, 2-light TIRF, I have it here. I should be prepared, but this is like kind of manual. I mean, for all this microscope thing. And then we have our 2-light TIRF somewhere around. Yep, 2-light TIRF. So this, we have red, we have green. Actually, we have 2 green. So what's the red? The red is the dichroic mirror. If I move this out of the 2, this 6. So I turn, and we have a 6 here. So this is what the 2-light TIRF really is. When it's inside the turret, it's going to sit in wrist orientation. We have our laser going on this direction. Laser coming on, and we have a mirror, which is our dichroic mirror, to reflect our mirror reflect our laser. And actually, we have a filter here. This is our excitation filter. And this excitation filter is our red here. And the red, it will pass through our blue laser and our red laser. So by 2 lights, you can use the blue laser and the red laser to excite whatever dyes you are using. Like we use blue for GFP and for like most of the Q-dot. And also we have green. The green is one of the green is the dichroic mirror, like this more fluctuate one is the dichroic mirror. The dichroic mirror here, it will reflect the blue. So the y-axis here is the transmission. So zero transmission means 100% of reflection. So if you have 0 transmission in blue and red, which means it's going to reflect your blue and red up. And then once your blue and red excite your dye, whatever, Q-dot, GFP, whatever, and then it will emit photons in different wavelengths, and will go up, collect by the objective, and then going back to this mirror. But it's in longer wavelength, that's called stock shift. So it's in a longer wavelength. And when you see in a longer wavelength, the transmission going very high to like 99% something. So most of the photons will pass through this filter. And also we have a third filter down here. That's our emission filter. That's in like the more sharp or steep green here. The transmission of the emission filter and the dichroic mirror here, they are all in green and looks like kind of overlap. But the real difference is the dichroic mirror is not very good at filtering out our laser. You can see like here, there's still like 1% of transmission for our for ADA if we use blue laser, which means when our laser going up and excite our dies, it will also reflect down, which means in our reflection we have our laser coming down, and we also have our dies, whatever emission, going down together. And the laser is brighter than our fluorescence, so we need to block the laser, and there will be pure fluorescence going through to the camera in this way. So the difference is the dichromator have like 1% of transmission, and this emission filter is like 7 OD, which means like 1,000,000%, 1/1 and 70. Only that amount of laser will pass through, which means we mostly block the laser and have very pure fluorescence going through this emission filter. And then we just put this back. And then we turn to 6. And then now we have our microtube again. I'm going to switch to this angle. This is, I have telescope and GFP, some GFP CBM from my cellular project. So again, contacts, and then okay, just push the air bubble to the periphery. And again, we need to find the surface, which is turn to the 1x, and then we're going up a little bit, or going down a little bit. Okay, let's going down. So right now it's like kind of a lot of bright field going through. You can see the background is white. So we need to turn off the IM, and then this is some some very high-tech thing just to cover so no light is coming through. You can do experiments with this light turning on. It's really high-tech. It's worth like $10. So it's totally black because we don't have blue light on, and we turn the light on. Whoa, that's a lot because I have a lot of GFP there. But yeah, you can see the intensity is going down. There's a lot of GFP and it's bleaching. So there is like also a lot of small bright dot here. That's my telespecs. So you can see intensity is going to rise shift because our GFP is not last long, and the only remain is telespec is because it has light.
They're both the same wavelength.
Yeah, about the valence, because we have the same filters, so whatever goes through will be the same valence. But the telespec is like combination of blue, red, orange, and far red. So like for the green and whatever else is going to be blocked by our filter, emission filter. But yeah, that's TIRF. Also, we want to like kind of have control to our TIRF, like what we did to our IM. So the control of TIRF is here. Maybe it's better to take from the side. We have this one and this one to adjust the position of this fiber. So when you're moving this and this, you're going to change the position of fiber like in this like up or down. So when you move this up or moving down and or this, you are going to change where the beam hit the objective. So let's say this is our objective, and we have our laser. Where's my laser? Where's my laser? So this is our laser beam. If your laser goes into the center of your objective, it's going to go all through because there's no reflection, total reflection. As you moving your beam outside towards the periphery, then the angle is going to increase because light need to like going up and then go to the focus plate, and there's an angle. As you're going out, the angle is going to increase, and then in a certain position, the angle is go to what called critical angle, and then there's total internal reflection. And you can go a little out. In that case, you're going to decrease the penetration depth. But yeah, that's how we have our TIRF. And please, if you go in this direction, there's another like aperture to change. We have this, and this is the aperture. So this is actually the field diagram. Again, it's very similar to the IM. Field diagram is like how big the area you want to illuminate, to excite and ensemble. And if I close a little, please. Yeah, you can see the change in the edge of the camera. So I turn it off, and then it excites like smaller, going up, going down, going out. So that's our field diagram. And also, this tool is to adjust or to centralize the aperture onto the camera. So if you find the field is like kind of not in the center of that movie, you can adjust this by maybe you can adjust it. So I'm adjusting. You can see how it change the illumination area on the camera. So I'm moving like to the bottom left and going back. So yeah, basically you need to center and this, and that's one thing. And at this point I need to turn the light off to show how the TIRF works. So please have you go this way, and be safe, leave some room here. So right now I'm changing where the beam hits our objective, and then you can see this is like it goes to if it goes to the center, and then it will go directly out of the objective. And I'm moving the beam a little out to the periphery, outside, and then the instant angle increase, and it goes down, which means, so right now this is going to be our reflect angle, right? So it increase, going down it increase. So going down and then boom, nothing goes down. That's our critical angle, and we have total. I can do it this way. So yeah, this two, can you see it in the camera?
Yeah.
So let's try it again. I forgot this one. It is. Yep. This is this one is changing the angle, going up and down. And this one is kind of adjust in different direction. Yeah.
Okay.
but we mostly change this line going down, and then let's see how it changed curve.
Is this postmark for something?
What? Oh no, I need to make a new marker there because I moved this table and that's like the old one. So I'm going to change it. So if you say if the beam goes to the critical angle and then you keep moving, and now you can see it's going out of the objective, which means it goes to the edge of the objective and no light is going on into the objective, so we lost our illumination. Right, you see? You're going out too far and then you lost it. So maybe I want to keep everyone in dark. That's why I have this one. Oh, you can see this. So actually it's a little off because I changed it. Move it back. See, because we have already bleached the center part, and then you can see it's still very bright in the edge. And it's interesting because like if we turn off the laser, and then if you have like multiple motor and it will come back to the center region, and once you turn on the laser again, it's going to like have high intensity back. That's called a fluorescence. Yeah. So you can see it here, and I normally go and make it just wider than the field of view. And in that case, we bleach like minimum. Guys. And then let's see what's the difference. So one thing is by TIRF we only illuminate a very thin layer of our dye. If we going into the what called dirty TIRF, which means to increase the depth of your energy, and then you will see the background increase as I go into the dirty TIRF and the avid, right? The background is increased, and yeah, that's TIRF.
We don't want this.
What?
We don't want this thing.
Yeah.
Sometimes people want.
Yeah, sometimes you want to like go in depth into a cell, something like that. If you want to do like cell structure or something like that. Because for normal TIRF, we only have 200 or 300 nanometers. And that's the one I hopefully no one is going to change it, or at least let me know if you want to fill or change it. So yeah, because there is like a certain spot that the single noise is maximum,
This is best for the single one.
and I need to calibrate and find that like sweet spot for TIRF. So that's TIRF, and currently we use two light TIRF but it's very easy to switch to like the other laser because right now we have three laser. We have green, blue, and red. And our two-light TIRF, we cannot use green because green will just pass through everything. So if you want to use green, you might need to switch to some other cube filters. And I'm going to make a table of all the other filters so everyone of us know what's the parameters, what valence, what size you can use. So yeah, this is adjust the focus. This is obviously. So this is to switch between the port. So we have one port here. So this port is for connection of camera. We can connect camera here. Also we can connect it here. And also right now we have in the left side. So this is going to decide which port the light is going out. So don't freak out when you see nothing over there. It's just because somebody else might accidentally touch it or do it in purpose. Who knows?
So the right port is
Going to be 4.
4.
It's kind of weird, but I think it should be 5 left. I don't know. Based from this table, it's like 5 is the left pole, but maybe this is like shift a little bit. Just remember 4 is the default and don't touch it. Hey, you are about right time. We're talking about the most important thing here. So there is a special mark here. It's possible then when you move the stage, and then it will push the objective to move a little bit. I don't want to show it, but you can see it's movable. It's easy to move. So which means if you move the stage towards this direction, far distance, it's going to push this. And which means the objective is off alignment, and we have nothing there. So obviously. So remember, if you you have your example, you have the sample set up and see nothing on this on the screen, then there might be you need to find the focus plane. But right now we have a very easy way to find the focus, and then maybe the objective is off alignment because somebody else might just do his experiments and never look at his hand, and maybe it's this port, and maybe it's the filter set. That's like all the possible play you want to check in. And
this is the actual lasers. So this is really have one bulb turned on, it's only showing up laser power, preset laser power for your 2 ways to type it. And this is the actual software. Okay, so when it shows up, you have your temperature in the bottom left here. Make sure cooler's on, set to -20. And then it's just gonna be a blank screen, it's not actually active. First, you can go to, where is it? Acquisition setup. Here you have your frame per second, your exposure time, this is your frames right here, so how many frames you want, your EM gain down here, everything else you don't really have to change. Here is where you actually go to save it, so this is your file name, make sure it's at TIFF. Location, you can set your file wherever you want to save it to. I think that's pretty much it for here. Yeah. And so then this is going to be, let's see here. Yeah, so this is going to be live. So now it's going to go to a live image. You have your scale up here, all your counts, so you can change this set your contrast and everything. You can also, if the range isn't big enough, you can move these sliders, change the actual range of it to whatever contrast you need it to. There's also this just helps change contrast even more for the sliders. This is to stop going live, go back to live, and then this is going to be to actually record the video. When you're done, go here, make sure it's -20, and then turn that off. And then that will stop the cooler on the camera. And then 5 minutes and you turn the camera off. And that's basically
basically the power off is the invert of the power on. We don't want to take your sample off when the laser is still on, because there might be a reflection and will go to your eyes. So laser off, and you can turn this switch off, or sometimes I will just leave it on. If you leave it on, when you turn the main power on, it will just automatically on, so you don't need to turn the second switch. So this is safe. If you have IRM, just turn it off. So this is on and off switch, and this is for the stage. I know there is also a switch over here. I normally leave it on. This is also okay because we will have our main power turned off. But remember, if this is not controllable, which means somebody already turned it off, even if you have the main power. I mean, I just made it complicated, but just to
make sure the switch is on.
Yeah, just to make sure it's switched on. Yeah, it's like kind of. Yeah, but I mean, this and this is safe to have it switch on. And then we turn up, just remove our sample gently. Sometimes I need a twister, but yeah, that's another thing that might damage your objective, because we know that objective is made of very like hard glass, cord or something, or blue stone.
I think it is.
Or something like that. It's very, the hardness is very high. Yeah, exactly. So which means like only the comparable hardness material will make a sketch on the surface. You are not going to make a sketch on this metal with your finger. It's like when you cut the glass, you need a very special diamond knife, because the hardness is like harder, so you can make a sketch. So I don't want to say that, but it's like generally it's safe to remove any oil or dirt on the objective. But practically, you need to make it like as gently as possible. I would like to, that's recommended from Thorlab. I never do that, but just to say that's the right way to do it. Put this over the objective, and you put a drop. So when you put a drop, it's going to contact with a drop, and just put it slightly. That's the right way to do it. But again, I said before, just so you know what's the best way to do it. Yeah. So that applies the minimum force as you drag it, and also it cleans the surface. I'm getting tired, so you're going to cut this part off.
Okay.
So the normal way I do is this Q-tip. Just put like a drop. We don't need to do much because there will be residues. So I rotate from the center. And
Textbook.
yeah, also just rotate from the center. You are not going to do it like this way because it's going to just mess up. You start from the clean from the center and then just repeat it like 2 or twice. And then this ring is like designed to collect any oil. So there might be like a lot of oil remain here. So remember to clean, make it clean. And yeah, that's cleaning. Straightforward.
We don't have a cover for this one, right? So that's
Yeah, this maybe is
Oh,
this one.
yeah.
And then we have our camera still on. Because so the idea of like turn the cooler off and then turn the camera off later is because if you like suddenly turn the whole system off, the chip inside this camera could be very cold, and there will be help me out this
condensation.
yeah. So there will be like
Condensation.
Condensation.
Where it'll moisture will start.
yeah, moisture will build up in the chip and it will just damage to the chip. But if you turn off the cooler and let it like go back to room temperature and it's equilibrium, so when you turn this power off, there's not going to be any
So how to
water.
turn off the cooler?
There's two ways, like in the soil is that just so that. But if we are using the micromanager, because we default set it to 70 minus 70, so you just set it to like 20 or 10. So let's see, temperature set point, just set it to like 10, it's safe enough. And it will just turn off the cooler automatically in the system because you set to a higher temperature set point.
Yeah.
I think that's like a more straightforward, like turn it off, but I can't find it. And yeah, once you set the temperature on to like 10 degrees Celsius and then wait for like 5 minutes, that's the time you're going to like clean up the objective and remove anything you bring in.
Save all the videos.
Yeah,
That'll take more than 5
yeah,
minutes.
and then
anyway.
you can turn it off. So there's a button here. Just yeah, I can feel it with my glove on top. Yeah. I think you really need to pay attention for the camera because if you like leave it power on for a long time, it's not good. It's also it's the most expensive thing.
Of the cameras that we have.
Camera is like really expensive, and for both this camera and even the iScape button. Yeah, and so now we make sure this is turned off, and then we have a manpower here. Actually, we still have our laser on. Just we turn the shutter out, so we don't have laser going through our objective because. The blue laser switch to standby, and the red so just turn it off. Yeah, it's already off, and you can have this turn it off, and then the manpower. Then the manpower is kind of safety protection for like in case you forgot to turn off something.
Yeah.
So this is going to help to turn everything off, and yeah. I think